right, and now we're to our wrap-up video for section 2.6. So, I told you what I thought we were going to learn, and then we went ahead and reflected on direction fields to kind of build intuition for approximating differential equations graphically. We connected what we had done in direction fields to what you already knew about making numerical approximations by using derivatives. Linear approximations is what you called them, or tangent plane approximations. And then we kind of brought those two things together and we talked about how we're going to find numerical approximations to ODEs, saying that it's connected to those two ideas and specifically that we use Euler's method to do it. We wrote out the steps for solving a particular differential equation. And then we looked at our first example, made sure to connect f's, x's, h's, and all that to a concrete initial value problem. And then I took a second to just tell you some things that I think you need to be careful about that I've noticed go wrong. And we wrote the Euler's method in kind of its generic step form, which some people find helpful. And then talked about what we get out of this, approximations to a solution to a differential equation, and two different ways you might calculate error to quantify how good what we get is. And then we set up the logistic example, said it's very tedious, and we worked on the spreadsheet thing. And I talked to you about your project, which you're going to use the spreadsheet for. So I've written right here the points that I think we covered, which is we approximated dy dx equal f of xy from some initial point using Euler's method. We spent a lot of time talking about how Euler's method works and how it's similar to tools you already know, just because the most complicated thing about this section is understanding what it is we're actually doing. I'm sure that you could sit down and apply the formula countless times, but the new material is really what it means. And then we did that computational implementation that takes us away from the arithmetic kind of task and then gets us really producing some nice plots. So I do want to say real quick that the differential equation that we solve using Euler's method does always have to be in that form, dy dx equal f of xy. So it doesn't work for like second order differential equations or anything like that. And you have to rearrange so that you have dy dx on one side, f of xy on the other. But our practice problem is going to start to set you up for your web work this week. So I don't want you to actually implement Euler's method just yet. I want you to look at this initial value problem I've drawn. Probably yours is going to be different. Y prime equals minus x plus y, and y of 3 equals 2. And I just want you to identify f of xy and x0, y0, and write the formulas for x0, or sorry, not x0, x1 equal to some stuff, and y1 equal to some stuff. You don't actually have to compute it. Use like h equals 0.1, I guess. I don't actually know what your web work does. Web work uses 0.2, so go ahead and start getting practice with that, I guess, on the off chance your symbols are the same. Just what's important here is that I want to make sure that you know how we pull information from the initial value problem to set up an Euler's method problem, and then just to write the first formulas to kind of see what's going on. So get to work on that practice problem, and I will see you in class on Tuesday to discuss it.